Careful. Do you want to turn it up a bit?
Can people hear me? Yes, no, maybe so. Can people in the back hear me? You turn the volume up. Crank the volume, Hayden. Why is this not turning up?
As high as it is.
Something is wrong.
Something is probably We can hear you, Lily.
Test. How are we doing back there?
Something is going through the speakers, but it's...
Yeah, it's... Are they definitely all plugged in back there? This is entirely cranked, so I don't think we can really go any higher.
It goes louder.
It should. It has in the past. I'm sorry, I'm just going to keep talking nonsense at you all while we figure this out. Okay.
There's 2 volumes.
Try the different... There we go.
There we go.
Channel 2 works. Would not be space drafts if we didn't have just a tiny bit of technical difficulties, so hopefully that will be the last of it for the night.
I don't know.
Can people in the back now hear me? Cool. Excellent. Thank you all for joining us tonight, this almost Thanksgiving. We are very thankful to have you here. So for those of you who have joined us in the past, welcome back. If you are new, welcome to Space Drafts. We are part of an international network of astronomy on tap shows, which are held by astronomy departments across the world in pubs and bars, where we get to bring the joys of space to all of you, the general public. Some fun things about the show here in Tucson specifically is that you may notice we are right next to an active train track. Thankfully, one has not gone by yet. But if one does go by, it is inevitably going to blow its horn, and it is inevitably going to make it so we cannot hear whoever's speaking. So if that does, the speaker will hopefully stop and prompt you all to raise your glass and wait it out, and also toast the train and say, what do we say? Choo-choo! Hopefully that will not happen more than once during a given speaker's talk. I am joined here tonight, so I'm Lily Whitler. I'm a PhD student at Steward Observatory, and I'm joined here tonight by a whole lot of my co-organizers. If you would raise your hands, please. One of whom is also giving a talk. So any of us, and also our speakers, will be happy to talk space with you during intermission after the show. Is there anything else? I have a list of notes here that I should have had pulled up and absolutely did not, because I will inevitably miss an announcement that I need to make. Oh yes, so the way that this show works is we have 2 approximately 20 to 30 minute talks, interspersed by a 20-minute intermission. So we'll have one speaker, 20-minute intermission, then another talk. We also have some merch over there, some pint glasses, some stickers, some magnets, I think, unless we've sold out of it. So feel free to come talk to us during intermission or after the show, and we'll be happy to take your money. Also, please tip your bartender. The Borderlands here is very kind to host us without any charge.
So do eclipse glasses? Eclipse glasses?
Oh yes, we do have eclipse glasses. We're giving away free eclipse glasses. There will be a total solar eclipse transiting the United States in April, and we'll get a partial solar eclipse here. Do not look at the sun without the eclipse glasses, please. So to save your eyes, we are giving away free eclipse glasses pretty much now until the April show, when it's not worth it anymore. I think the next eclipse that's going to the U.S. is in like 2040. So if you want to hang on to your eclipse glasses for 20 years. On that note, I will introduce our first speaker, another Steward grad student, Haley Bowden, who is going to start us off by talking about the past history of dark matter. Thank you. Hi everyone. I am here to talk to you about the dark history of matter, by which I mean the history of our study of the stuff that we call dark matter. The matter itself is very dark, the history not so much. I was in a spooky mood when I wrote this title. So, to get us started, immediately.
Told you. Hold on. Put the
Is it on? Is it on? How do I turn it on?
Is the PowerPoint forward?
This guy? Okay. Thank you.
There we go.
So stop. What is dark matter, or what do we mean when we talk about dark matter nowadays? So a lot of you are probably familiar with dark matter, or and a lot of you have probably heard of dark matter, but are less familiar with what it is. Hopefully we'll learn some along with the scientists as we go through our history, but just to start us out on kind of the same page when we're knowing what we're talking about. When we're talking about dark matter, is what we call this stuff, this matter that makes up 80% of our universe, we think. And, 80% of the matter in our universe. And that is, it does not interact electromagnetically, which means we can't see it with light, but it does interact gravitationally, which is how we're going to get our big clues towards its existence. I think that's enough to get us started and on to our first trivia question. So I have some history trivia for you. When did the term dark matter first appear in a scientific publication?
Raise your hand if you have a guess.
1922.
Yes, you are correct.
Can you say it? The answer?
So the answer is 1922.
Wow.
So 1933 is sometimes quoted as the correct answer, but this is when Fritz Zwicky will start publishing papers about the coma cluster, which I will talk about we'll get to in just a second. But actually, way back in 1922, before the whole dark matter craze, there's actually a reference to dark matter in a paper by Captain, whose name I can't remember, so I had to write it on my hand. I'm sorry. But he wrote a paper about about dark matter in our universe, which he was referring to the Milky Way, with the sun at the center. It's an interesting paper if you want to read it. But he refers to dark stars and later dark matter. What he's probably referring to is what we would now call black holes, or something kind of closer to that idea. But it is the first. It is the first. It is the first time that appears in a publication. As far as I can tell, I'm a historian. I'm an astronomer, not a historian. But if we do speed forward to the 1930s and to when not only are we pretty sure there's other galaxies, but we've also found galaxy clusters, like this one. We run into this character, Fritz Zwicky. I really hope that he had a sense of humor, because everyone uses this photo of him, and it's not like the most flattering, but it is amazing. Like, it is really good. And so Professor Zwicky was a professor at Caltech, and he made a bunch of observations from at Palomar Observatory of galaxy clusters, like, go ahead? Okay, no, like this one up here. And one thing that was interesting about observing these galaxy clusters is, I'm sorry, I've lost my train of thought. Looking at galaxy clusters is similar to looking at things at other scales in our universe, like looking at a galaxy or looking at, say, planets orbiting. And if we consider, for example, a satellite orbiting the Earth, or our galaxies in our galaxy cluster orbiting the center of the cluster, we have a similar idea of how gravity works, where if we're talking about a satellite around the Earth, it has to be going at a specific velocity to stay in orbit. If it's going too slow, its orbit will decay and it'll crash into the Earth. If it's going too fast, it'll just be thrown off into space. So, Zwicky is looking at these galaxies in this cluster and looking at the velocity dispersion, so like the range of velocities that we have with these galaxies in this cluster, going, they are moving way too fast. Why isn't this cluster torn itself apart? Why haven't they all just shot off into the wind? And idea being there should be a lot more mass here than we'd expect. If you just look at the amount of light that we're getting from these galaxies and from this cluster, that gives us a certain picture of how much mass there is and how fast things should be moving. That does not fit with our picture with his picture of what he was observing. And so he suggests maybe there's some invisible matter here, just some things that we're not seeing. Maybe it's gas, maybe it's really faint stars, maybe it's something we don't know about yet, but there is there is matter missing to make this make sense gravitationally. Now he has a couple landmark papers on this subject, and then it lays somewhat dormant for the 40s and 50s, where there are a scattering of papers about cluster velocity dispersions, but not a ton of new information, until we get to the 60s and 70s, where we start to get some really interesting observing technology going. And especially in areas like X-ray astronomy and radio astronomy, we start to be able to do some pretty cool things, including the work that Vera Rubin did in the 60s and 70s on observing galaxy rotation curves. So I have a brief interlude on Vera Rubin because she was a very cool lady, and did a lot of pioneering stuff for women in astronomy, and just a lot of pioneering stuff for dark matter and the advancement of astronomy in general. So she was the first woman to observe with the Carnegie telescope at Palomar Observatory. She started early on in her astronomy career to look at these galaxy rotation curves. At that point, there was not a ton of information about this. But one thing that's cool that you can do with radio astronomy is, instead of just looking at the light from the stars, you can actually look at the gas in the galaxies, and specifically the neutral hydrogen gas. And what they're able to do with that is to plot the velocity of the gas as you go out from the center of the galaxy to the outskirts of the galaxy. And what was expected, based on how we understand gravity and how galaxies look, is that as you go out to the outskirts, the velocities should fall off and just like approach zero eventually. And what was found instead was what we call flat galaxy rotation curve, which is you can go way out into the outskirts of the galaxy and you're still observing these high velocities. And so these results start coming in, these flat rotation curves. At first, just a few of them. So thought maybe this is something specific to the telescope. There's some sort of error going on. Don't really know what's happening. More and more results come in across multiple telescopes, different research teams looking at different galaxies. Everything's got a flat rotation curve. And you get to the mid-70s and people are like, okay, there's flat rotation curves. We got that. We're not super big on the idea of dark matter. We haven't really connected this back to Zwicky yet and his clusters. But we're agreed like something weird is going on here with these galaxy rotation curves. And but very quickly, people start connecting this to our picture of missing matter. Maybe that is what's going on here. And we get some more evidence as well through, for example, through X-ray observations. This is a way of looking at the hot gas in a cluster, and another way of basically getting a similar idea to what Zwicky had found about this missing mass in clusters. Similarly, we're also getting observations of gravitational lensing, which is the idea that there is if you have a foreground source, an object, and you have another object that's emitting light behind it, and that foreground source is really heavy, the light from the the background object will be gravitationally. I'm missing a word.
Bent?
Yes, thank you. Gravitationally bent by this foreground object, and it creates these arc shapes on our images. This one on the left is cited as having an arc, and I think it's right up there. I don't believe if you can't see this. I think this is a scan of a PDF of a scan of a PDF on a projector. But if you look at a modern day image, you can see all of these arcs here. So that's kind of what they're getting at. And this gravitational lensing also tells us about the mass that's there, and tells us that the light that we're seeing from the stars is not representative of all of the mass that is there. So we've reached 1980, and around 1980, most astronomers agree, reluctantly because it makes things complicated, but they agree that dark matter exists. But what is it? One suggestion? Squirrels. I just thought you'd appreciate that for a second. Do I want to read the panels? Oh, okay. So it says dark matter density in the solar system is around 0.3 gigaelectron volts per centimeter cubed. Is that a lot? In terms of mass, the Earth contains 1 squirrel worth of dark matter at any given time. Wow. Is there any way to find out which squirrel it is? No, it's not literally. Oh, that explains why they weigh enough to set off those spinning bird feeders. Dark matter isn't squirrels. So that's up for debate, but one thing people did start discussing about what dark matter is it hot or is it cold? And this is kind of one of those weird things where physicists say mass is the same thing as energy, is the same thing as temperature. But the idea is that if dark matter is made up of little particles, like normal matter is, then maybe those particles could be either very, they could be very hot or very cold. So on our hot end, what we have proposed is people have heard this idea. Particle physicists have found neutrinos, these massless, like fast-moving objects. Maybe we have neutrinos that have a little bit of mass, and they're moving very fast, and that can explain all of dark matter. They just don't interact. On the other end, we're like, okay, what if instead of that, we had very massive particles, with a lot more, moved a lot slower? Okay, these are two great options. What on earth does this tell us? How could we have any idea of probing this? And the cosmologists come up with something kind of interesting. So, from a cosmology angle, we can look at the way that we can look at the early universe and the role that plays in how structures like galaxy clusters and even larger structures form in the universe. And an interesting thing about our dark matter particle in our cosmological models is that if we have a very low mass particle, if we have hot dark matter, then in the early universe we form these very big structures, and then over time those structures will fragment into smaller structures until we get down here where we have like galaxies and galaxy clusters. So start big, fragment into small. This is our top-down approach. On the other hand, if we have a more massive particle, we start with smaller objects in smaller structures in the beginning of the universe. They merge or they create matter from other things, and that is how we end up with larger and larger structures over time. And the cool thing about these two pictures is that they actually have observational implications for the distribution of galaxies. So, I'm afraid to say that hot dark matter had a very short life. In around 1984, people were pretty much agreed that the observations did not support the existence of hot dark matter. And So maybe cold dark matter is the one cosmological model to rule them all. It keeps lasting. It lasts through the 90s when discovered the expansion of the universe is accelerating. You know, like, oh, we gotta add some dark energy in here. Don't worry about it. It's something different and magical. It lasts till around 2000 when it becomes generally the standard cosmological model. Here is our lambda CDM. Lambda for the dark energy part, don't worry about it. And CDM for cold dark matter. I can tell you I use this model in my simulations and all my papers. It's very good, I like it. No idea if it's right. The cool thing about it is that we have we know a lot about it. For example, we know that it's cold and we know that it's dark matter. Hopefully Hayden in the following presentation can maybe tell us whether we're even right about that statement. So because I really like the name dark matter, but some people don't. So I consulted with my good friend thesaurus.com and came up with some alternate name suggestions. Feel free to share your opinions on these, or if you have any other suggestions of your own afterwards. So I suggested somber matter, drab matter, gloomy matter, sinister matter, and my favorite, secret matter. So these are just, I'm just throwing these out to the community. You can all discuss. Make sure to give me credit. So to just end off, I want to give just a quick overview of what our timeline looks like, because things kind of moved in interesting spurts. So we have our 1922, this term dark matter appearing, but doesn't really mean what we think it means. Finally, we get 1930s, and as Mickey comes around, he's got some cool clusters. They are missing matter. But we don't really know what to do with that until we get to around the 60s and 70s, when we start finding flat rotation curves of galaxies and finding that galaxies too are missing matter. And we also are getting more observational evidence for this missing matter, such as X-rays and gravitational lensing. And then by 1980, scientists are pretty agreed, dark matter is here. They start coming up with theories, lots and lots of theories. There is an overwhelming abundance of theories. And eventually we end up in 2000, and kind of still today, several decades later, with lambda cold dark matter as our standard cosmological model. So yeah, that is what I wanted to share tonight. Thank you all so much. If you want to take away anything extra, this is a link to the dark matter rap. It's formerly known as Cosmological History for the MTV Generation, by Professor David Weinberg. He's written some really good literature on dark matter, but also this rap. It is unfortunately way too long to include in this presentation, but I encourage you to look it up. I also encourage you to check out some of the sources that I used to prepare this presentation, because again, I'm an astronomer, not a historian. But these are some very cool sources on the history of dark matter, and this last one is specifically about, is a short little autobiographical piece about Farrah Rubin that I definitely recommend reading. So yes, thank you everyone. Questions? How cold is cold dark matter? That is a very good question. It's not hot, so it's not these low mass neutrinos that are like 10 electron volts or so. Hayden might have more to say about this in the next presentation. There's not, I would say, super specific constraints on what this is. There are various observations that support certain certain ranges of masses, but I don't know them off the top of my head. I'm sorry, but Hayden, come around to you. Sorry, I'm passing it on.
That's all good.
Um,
You can do it.
Yes.
I had a question about superclusters.
Superclusters.
Yeah.
Okay.
So I saw something about the Virgo supercluster, and that made me think of the Laniakea supercluster. Is the Virgo supercluster a part of the Laniakea, or are they completely separate?
I have absolutely no idea. I'm sorry.
It is.
Oh, it was a question about the Virgo supercluster and the linear K.
Yeah, Laniakea.
Okay. And
Come ask out over here. There's some other
yes,
other astronomers over here that might be able to answer.
Solis says yes.
Okay, so it is a part.
Yes.
Okay.
Yeah.
Alright, cool.
There's a
Thank
question
you.
in the back.
Yes. So like non-dark matter theories. I mean, a lot of people like to bring up alternate gravity theories, but we've got a lot of evidence for Einstein's gravity that's turned out pretty well. Dark matter really fits our observations quite well. So it's what dark matter is up for debate, but I would say the existence of dark matter is fairly well agreed on. There's not a ton of other scenarios out there.
One more question.
I have one more question.
Yes.
Why is Ziki's portrait that bad?
Or that good.
Why is Vicky's portrait that bad or that good? You know, I have no idea. I think someone caught that photo and it's just like collectively from the time it was taken till today, everyone has decided it's the most amazing photo and they have to use it in their presentation. He,
One of these early astronomers like the gym.
I don't know that he was a gym bro. He was known to be somewhat of a loner and a curmudgeon. So I would say that maybe he pissed a few people off, and that might be why.
I think curmudgeon with a capital C
Yeah.
is the best description.
Yeah. Okay, thank you, everyone. Thank you very much, Haley. For being an extragalactic astronomer, I actually know like not a lot about dark matter, and certainly not a lot about the history. So I hope you learned all. I can talk. I hope you all learned as much as I did. So it is now 8:01. We will go on our 20-minute.
You can do it, Lily.
20-minute intermission now. So
Perfect timing.
there's a train coming, so I'm going to talk fast. So let's just call it 8:20. Please be back by 8:20. Take your bathroom breaks. If you get a drink, please tip your bartender. Feel free to come talk to us. Feel free to come and ask your question. I'm going to stop talking now before this train comes. See you in 20 minutes.
There was literally a Mons paper last week,
Oh yeah.
and I wanted.
Yeah, it was the wide binaries thing
Wide
with
binary
Gaia.
one.
Yeah.
I was trying to come up with some snarky way to ask about Mons, but I couldn't come up with one.
Well, if you do,
Literally last
feel free.
week, there was that binary paper.
Yeah, because I
I probably should know.
I mean,
about that.
you know what the conclusion was. Mons is not supported.
I mean,
obviously. Yet again, we can fail to confirm Mons.
I was doing galaxy dynamics in like the mid to late 90s. So like all my papers went through like Mon referees.
I am in a projected fight with a friend because he's very smart. He's like computer science, AI. Like he works on Watson. He's like an IBM AI genius guy, PhD, very smart. But he doesn't know anything about astronomy. But he's very smart. So he's like, he wants to be. He's a dear friend, by the way. Love him to death. But he wants to be like I'm like smart and countercultural. So I'm like, it's dark matter's not real. We just don't understand gravity. And I'm just like, boom! Like I'm in like a projected fight with him because He won't give it up. I'm like,
theory-
we are in a fight.
Our theories of gravity have passed every fucking experiment for a century. It's like
Even Einstein's
special
biggest
and
blunder
general.
wasn't a
Was
blunder.
right. It was
was not
so
a blunder.
Special and general
ridiculously
relativity.
creepily incorrect.
Yeah.
You heard my rant.
It's a good rant. I support this rant.
Hey, what have you been doing?
What?
Trying to find
the pop filter for the microphone.
Oh. It's there.
Yeah.
It's on the mic
Now
now.
on the
Bet.
microphone.
Let's never take it off.
Fantastic.
Only been
Oh, live streaming rants was fun.
You hear my story about being in a fight with my friend.
I should probably go sell merch. That is in fact my job.
Oh, I found my drink.
So Lily's over there.
I'm
Like a
coming.
champ. I'm gonna get another drink. Huh?
Want me to save you?
Hey, got your glasses. Yeah. Look, there ain't just on top.
Oh, but it won't happen like it.
Yeah, it will.
Any plan? Well, I was certainly get it like campsites and to our parents' house because there's always possibility that weather's not
How's the job hunt? I heard you talking to somebody about it.
I'm seeing it all the applications. So
I still have a few like individual ones, like applying to like a specific person. Last year, otherwise all the other ones.
I think the fellowships are generally. I actually already got my first rejected.
You did come
Yeah. That was MIT Capital Art. That was pretty early. Yeah. It was due like on October 6th.
Yeah, that's when 51 Peg was due. And I asked Jared, so 51 Peg is due October 6th. And Jared is 51 Peg person. He's awesome. The coordinator for it and all. So I was like, y'all meet? And she's like, oh yeah, a long time ago. And then he was, but apparently 51 Peg is like the last one to like put out the pages. So like the first one is due.
Like after Hubble?
Yeah, I think so. That's cool.
Well, private money.
When I was in California,
Yeah.
I learned that the Hayden Foundation was like a couple blocks down from my school. Yeah, I was like,
Headquarters?
yeah, I was like sitting, I was like looking at something and I saw the address of Los Altos, California, and I was like, I know Los Altos. So I Googled their location and I was like, it's on my street.
You could actually just hand in your application.
I know. I was like, can I just like go knock on their door and say, money please?
Yeah.
Give me money.
Yes.
Oh, I was asking for Anch.
Oh,
Anch.
Oh my god!
He was so excited to come out one day. This was the first time.
I don't have the full beard. I don't have the glasses. Or I can start a chat.
I can just feel it.
I didn't realize you already cut the part when you said like.
I said I got cut. I said I got cut.
But I didn't know. I didn't hear that earlier. So yeah, you're literally announcing to the world just like that. And so yeah, oh yeah, go ahead. Yeah, I'll go with. I'll just go with you. And then he's like, oh, same I'm not going with you on this mission. It's a suicide mission. I thought you were saying you were gonna try. Yeah, not that you already had a balloon. Oh, you. Yeah.
I know it's fine. I say he's going to get it for I have.
That's how we get rid of our grass competition.
I almost ate it hard just now.
Uh-oh.
I managed to roll over my own toe. And I had one hand I saved it. 6 months of practice. The thing is, and they're hard. So any kind of puzzle, I'm like, I have gone like been to the front of this a couple times. And then it's like, I'm laying on the ground, like hurt, so embarrassed. And then there's like a million people. Are you okay? Are you okay? I'm just like embarrassed. One time I was like so rude because I was just like, stop, like leave me alone. Like I know you're trying to help, but you're making it so much worse, you know? Like
Let me just die here.
I'm sleeping in my seat without being and I felt bad because like they were distracting me. And so I had to be like, I'm sorry, I'm just embarrassed.
This is your 5-minute warning. We will be back with our second speaker in 5 minutes.
So yeah, that happened a couple times. I'm getting better though. Also the handlebars came in it's built to fold up. So it's got that joint there.
It's kind of flimsy though.
Yeah, right. So as time has gone on, it's gotten more and more wobbly.
Got more play.
Which really sucks. I've tried to tighten down as much as I can, but it doesn't make a difference. Ooh, that's good.
What is that? Vino?
Yeah, it's just a red blend.
Huh.
Super good. No, I was not impressed with the margarita. So here's a good example of how I think we should implement what AOT Austin used to have, which is the name tags. They had name tags, and everyone had like, of course they're always late.
Oh yeah, don't get me started.
They've come to our generation.
I know.
But yeah, they had name tags, and then they're called Space Cadets, and then everybody has like a nickname. Have you seen how Jackie and Danny are like, I'm AKA Whataburger Jr. and it's Travis? That's from their
Right. Yeah.
But having the name tags, then somebody would say, the host would say like, feel free to ask anyone with a name tag any of your questions. You know, want to chat about astronomy more? Go find someone with a name tag, right? And they would put like their specialties on there.
I found out that one of my collaborators on Spec Reduce, Claire, is like college buds of Jackie
Oh.
when they were undergrad.
Wait, Claire was here?
Claire Shanahan,
Yeah,
yeah.
I went to choose trivia.
Oh,
We go to
okay.
trivia on Mondays, and we always have 5 people, and you can have 6, so Jackie brought 4.
Okay.
To our,
Yep.
our last game on Monday.
Yep. She was in town for the same.
Yeah. That's cool. That's fun.
Astronomy is a small town, man.
And there really are like 5 people in the world. 8 people.
3 degrees from Fish Boy.
Really. Yeah. But yeah, I think that's a good. I think this is a good example of why I think that would also help foster interaction.
Yeah.
I know, I realized.
We don't have to do dumb nicknames if we don't want to, but they're fun. Mine was eccentric orbiter. What a Bridger Jr. That one is so good. Because like the junior just sets it over the top. Because we were in Texas, of course. Very important. What a Bridger Jr. It's so funny.
So I was so wigged out when I was at Sci-Fi and there was an In-N-Out burger like literally across the street from the UT campus. I'm like, wait, what?
Yeah, they
That's just like the two locomotives.
Yeah, that was just
Ball.
yeah, they moved in like, I don't know, 10 years ago. They're no longer special. You can get them anywhere now.
I know.
It's no longer something you get when you go to California. You can get them anywhere.
But it's just like,
But also, Whataburger is is one of the few like very Texas things that I will not defend. I do not like Whataburger. I do not like Whataburger. I do not get it. I don't understand why people are obsessed with it. I don't get it.
I'm ready to go. We just need to open the projector and then
Having the PhD, yeah, I think helps.
I got the slides swapped over. I am.
Hayden, is this as big as your slides are gonna get?
That might be.
Yeah, actually, I had back-to-back meetings in town last 2 weeks. No, in Tucson. Actually, was living in the van at the RV park on Grande. Well, it was either that or commute from Dump Mountain. So,
What about your house here?
we don't have a house here. That we were renting
You're
that.
not in that weird house anymore?
No.
Every time I drive by that house, I'm like, I can't believe Tim lives there.
I don't live there anymore.
You didn't? I didn't know you moved.
Well, the kid moved to the dorm, so we didn't need to pay rent there.
Yeah.
And then Carrie's mom had shoulder replacement surgery, so she needed like a month and a half of vision care.
So you live way north now?
So Carrie and the dogs are at her mom's house,
Which is
Dump Mountain, like north of, like 5 miles north of Tangerine Road, like by the Ritz-Carlton. So it's like 30 miles.
Hello, we are restarting. Please take your seats.
very factual. Very true.
Anyway, I was across the street from
I'm going to stay here
Whataburger.
in awkward silence
and
for
I
the next
swum there
like
a
30
couple times.
seconds while I wait for everybody to trickle back from the bar.
You gotta be cautious with this one. Yeah. You gotta be careful where you gotta.
Okay, I think we are at an equilibrium-ish here, so I am very pleased to, I have lost the word, introduce our second speaker.
We're having problems today.
I'm specifically having problems speaking today. I don't know why. It's fine. Anyways, so our second speaker is Hayden Foote, who is also a graduate student at Steward Observatory. And now that Haley has given us the rundown on the past of dark matter, hopefully Hayden's going to tell us about the present and the future.
Awesome. So Lily took most of my self-introduction out of my mouth already. My name is Hayden Foote. I'm a grad student here at Steward. And now that Haley has done an excellent job telling us about the history of dark matter, why we think it exists, what it does for us cosmologically, I'm here to try to get at this question, well, what is dark matter anyway? And I'm going to play spoiler for you right off the bat. If I can advance the slide.
That was my bad, I think.
There we go. We don't know. So sorry to disappoint you if you were hoping for an actual answer to that question. But what I am going to try to convince you is that this is actually better for two reasons. One, because it's much more interesting. And two, because it means the National Science Foundation will pay people like Haley and I to try to figure this out. Woo! So I'm going to revise my title a little bit here to what do we think dark matter is, and more importantly, why? And as it turns out, this is still a really, really hard question to answer. And the reason why this is a really, really hard question to answer is because dark matter looks like this. The projector is not broken. I meant to do this. Dark matter is completely invisible. We can't see it. So, luckily, as Haley mentioned, it does have gravity, and that means it influences normal matter, which, luckily for us, looks like this. We can see it. So, what I'm going to try to go through is how we use observations of stuff that looks like this to tell us something about stuff that looks like this. And so what this looks like in a nutshell is we want to start with what we know. So, as Haley mentioned, we think that dark matter makes up about 80% of the mass in the universe, and it also has gravity. And so because gravity is caused by mass, and dark matter is most of the mass, dark matter sort of acts as the scaffolding of the universe. And so the behavior of dark matter is going to very sensitively determine the sizes and the distributions of galaxies that we get in the universe. So that's going to be how we start to get a sense of what dark matter is. So we also need to come up with a bunch of explanations, come up with theories for what we think dark matter might be. And we need to test those to make sure that they are capable of reproducing what we see in the actual universe. So we try to use observations to rule out these different ideas of what dark matter is until we're just left with one. And so what this essentially comes down to in a sentence is we're looking for the simplest possible model of dark matter that can explain all of the observations. And so, since dark matter seems usually like a kind of daunting topic, I want to start off with an analogy for exactly this thought process that's hopefully a little bit closer to home. So just for the sake of thought, let's say that you get home from a long day of work and you see this. Okay, so we have an event here, something that we did not see, like our dark matter, which is that paper towel roll getting torn up. And this picture, what we can see is like our galaxy observations. And we can use the information in this picture to figure out what happened to our roll of paper towels. So, what happened to the paper towels? The first thing we need to do is come up with theories, ideas. What might have happened to the paper towels? And we can organize these on a scale from the most simple to the most complex. So the simplest possible thing that could have happened to our paper towels that doesn't require any other external factors is that the paper towels just tore themselves up. You know, it happens sometimes. You live with it, you move on, everything's fine. But we can introduce an external factor as well, namely this guy. Maybe he tore up the paper towels. I don't know, he looks pretty guilty to me. But, just for the sake of argument, let's also come up with something a little bit more complex. Let's say there's a paper towel bandit that broke into your house while you were gone, tore up all your paper towels, and left without a trace, just to spite you. And our next task is then to try to figure out which one of these is correct. So, in the case of our simplest theory, we can rule this out by appealing to the laws of physics. Because we know from the laws of physics that paper towels don't just tear themselves up, right? That can't happen. So we can take that off the board. In the case of our more complex theory, there's nothing that says this is physically impossible. It's totally possible for someone to break into your house and tear up all your paper towels. But why? Why would that happen? It's too complex. So it's allowed, but we don't need all that complexity to explain what happened because, of course, we have our very guilty cat who probably tore up the paper towels. Now, I'm willing to bet that most of you reached that conclusion pretty much the second you saw that picture. But what you didn't realize is your brain did all of this almost faster than you could think about it. And so what I'm trying to say here is that dark matter isn't this really daunting part of science. It's an interesting problem. And we use very common thought processes to try to get at what it is. So again, to summarize here, we're looking for the simplest possible model of dark matter that fits all of the observations. The only problem with that is there's a lot of options. So this is our tongue-in-cheek version. This is again from XKCD. So we have certain things like bees, or space cows, or maybe those orbit lines in space diagrams are real and they're very heavy. So this is a sort of tongue-in-cheek version of this, of course, but that does bring us to our trivia question. Which one of these is not a real name for a theory of dark matter? So we've got WIMPs, we've got cue balls, we've got fuzzy dark matter, we've got sterile neutrinos, we've got sponge dark matter, and we have technobaryons. Any guesses? Yes? F, it is not technobaryons. That's a real one. Good guess though. Go ahead.
There's no shot sponge dark matter.
Hey, you're right. That's the fake one. Nicely done. Come up and get a sticker after the talk if you want. So, this is the real version of that XKCD comic. This is what I like to call the cursed Venn diagram made by Tim Tate at UC Irvine. This is some kind of attempt to organize our theories of what dark matter is. And I don't expect you to be able to read this. I don't expect you to be able to understand it. I don't, and I do this for a living. This is just to give you an idea of the magnitude of the problem that we're working with. This is all of the different theories that we have to sort through. So what do we do when we're faced with a really, really complicated problem like this? We start as simple as possible with our cold dark matter that Haley told us about earlier. So just as a refresher, cold means the typical speed of our dark matter particles is much, much, much slower than light. We want these dark matter particles to be invisible, or at least dark, again, to match with our observations. And we also want these cold dark matter particles to almost never hit each other. So if we had two clouds of dark matter that moved past each other, we'd expect them to just move past each other without interacting. So there's two main flavors that people like to invoke with cold dark matter, so two options for what it is. And in a very rare, if I may say, spurt of creative astronomical naming, these two opposing theories are known as WIMPs and machos. So I'll go through what each of these mean here. So WIMP stands for weakly interacting massive particle. Now that's a lot of jargon, so let's break that down. Weakly interacting, for the purposes of our talk tonight, just means doesn't interact with light. This is what makes them invisible. Massive in this case means about 100 times heavier than a proton, and particle means it's still a subatomic particle. It's smaller than an atom, but it's pretty heavy as subatomic particles go. And the way we want to look for these is the way that we look for any other kind of particle. We build a really expensive experiment to try to detect its presence. So essentially what this is going to boil down to is coming up with different ways of being able to tell if one of these WIMPs interacts with an atom of normal matter. And so an example of this is the cryogenic dark matter search 2, pictured here. And like other searches for WIMPs, we like to put these really, really, really far underground to get them away from other kinds of particles up here like radiation or cosmic rays. So this particular one is in the Sudan mine in Minnesota. It's like 2,000 feet underground. And the idea behind this is that we're using a super cooled crystal, so we cool these down to a few thousandths of a degree above absolute zero. And we know that this crystal will vibrate in a very particular way if one of these WIMPs comes along and hits one of our atoms in this crystal. So that's one example. There's a couple other ways you can do this. So you could use a noble gas like this xenon detector, so that the noble gas will emit a flash of light that you can see if it gets hit with a dark matter particle. And we also have crystal scintillators like this Sabre detector, which do essentially the same thing but now with an ultra pure crystal. So particle physicists have spent decades pouring millions and millions of dollars into building all of these crazy things underground, and we found absolutely nothing. I think there was one group that claimed to detect a WIMP a while ago, but that's since been disproven. So despite all of this effort, probably not WIMPs, at least not as we first formulated them. So what about our other option, our machos? So macho stands for massive compact halo object. Massive in this case, just to confuse you, means somewhere a bit more massive than a planet. So somewhere in that mass range. Compact means that they are opaque, so not like a gas cloud. And halo object means these are larger astrophysical objects that sort of float around outside and inside of galaxies. So the idea behind machos is like, what if we have a bunch of real objects made out of normal matter, like rogue planets or black holes or brown dwarfs, stuff that doesn't emit light but we know exists. And what if there's just a whole bunch of this stuff out in galaxies and that's what's making up the dark matter? So we can search for these with something called microlensing. And Haley talked about gravitational lensing a little bit before. This is a slightly different flavor of it. What happens here is, let's say we have a macho, which is this yellow dot, and we have a star, a background star that moves behind the macho, which is this red dot here. And what happens is the light from that star will get bent around the macho, and what you'll actually see are these blue dots. And so when this happens, you'll see we get two images of the star as it passes behind the macho. And even though we can't resolve this with our telescopes, what we do see is this very characteristic increase and then decrease in brightness of the star with time. So what you can do, and what several groups did, was take a telescope, point it at a nearby galaxy like the Large Magellanic Cloud, wait a couple decades, see how many times you observe this, and then you can do some math and figure out how many machos must be out there in the Milky Way making up dark matter. And what you end up with is that machos can't make up more than about 1% of it. So we've sort of struck out both times here. So cold dark matter can't be WIMPs, it can't be machos, and as it turns out, there's actually another problem. One of the ways that we test our theories of dark matter is we can set up computer simulations that study the formation of the universe. So we can start with an assumption for what our dark matter is, put in some gas, let everything run, and see what kind of galaxies we get out at the end. And what we saw when we assume cold dark matter is that we have too many small galaxies in our simulations. So we have the right amount of large galaxies, but we've got too many small ones. And so I'll throw up a different simulation here in cold dark matter, and so hopefully the projector resolution is good enough to see this. But of course you have your big clumps, and by the way, this corner is just an inset zoom in of the center. But you'll also notice we have these really, really small clumps of dark matter as well that are hosting these small galaxies that we don't observe in the real universe. And so what do we do when we think our model is too simple? Well, we can add a little bit of complexity, some extra physics on top of this. So let's say, what if, instead of not having our dark matter particles hit each other ever, we can allow them to hit each other every so often. We get what's called self-interacting dark matter because it's now capable of interacting with itself. It behaves a little bit more like a gas. And when I flip back and forth between our cold dark matter and our self-interacting dark matter, hopefully you can see that we have fewer small clumps. So we've reduced the clumpiness of the universe just a little bit. Another way you can do this is by doing something somewhere between the hot dark matter that Haley talked about before and our cold dark matter. We call this warm dark matter. So it doesn't move quite as fast as hot dark matter, but it still allows galaxies to be assembled from smaller ones like we want. So again, if I flip back and forth between self-interacting and warm, you should notice, again, we're making the universe a little bit smoother. Lastly, we can reduce the mass of our dark matter particles all the way down until quantum mechanics starts becoming important and our dark matter starts behaving more like a wave than a particle. We get what's called fuzzy dark matter. And again, if I flip between, hopefully you'll notice, again, we're changing the clumpiness of the universe. I can start from cold and go down the line, and hopefully that becomes clear. So now we'd like some way of distinguishing between these options. And like I said before, we're lucky because if we change the physics of the dark matter particle, remember we're changing how that scaffolding that underlies all of the galaxies behaves. And so that's going to in turn change how the galaxies themselves behave. So as an example, in cold dark matter, we know that smaller galaxies orbiting bigger galaxies will eventually slow down and merge with those larger galaxies. And we like this prediction from cold dark matter because this is what we see. This is how we think large galaxies get assembled. So small galaxies tend to merge with bigger ones on some particular time scale, and this is what we want to be able to reproduce with our dark matter models. But for example, in self-interacting dark matter, if you make those interactions frequent enough to reduce the clumpiness of the universe like you want, all of a sudden, these galaxies get torn apart before they're able to merge with larger ones in clusters. So that's actually a strike against self-interacting dark matter because we don't observe this. As one more example, what about fuzzy dark matter? Well, if you make the universe fuzzy enough, turns out galaxies start to have trouble merging. So they will orbit larger galaxies for longer than we actually observe. So galaxies are now taking too long to merge, and this is a strike against fuzzy dark matter. So that's one way you can do this, and I've done a little bit of work in this area. But really what we want at the end of the day, the sort of gold standard for all of this is, again, the reason we came up with these models in the first place was to change how clumpy the universe is. So if you can measure how clumpy the universe is, then boom, we know exactly which model's right. So one of the more sensitive ways that we can do this is by using something called stellar streams. So when we look outside of the disk of our Milky Way galaxy, this is a picture from the Sloan Digital Sky Survey, and hopefully you can see this on the projector, but we see these thin trails of stars across the sky. There's a few of them labeled here. And these stellar streams are formed when star clusters that are orbiting our Milky Way get pulled apart. They slowly leak stars as they orbit and sort of leave them along the orbit of the cluster, and they make these thin trails of stars that we see. And these stellar streams are really good for telling how clumpy the universe is, because if you have a really smooth galaxy, something like warm dark matter, your stream is just going to sit there in its orbit happily forever. It's going to stay nice and thin and cold. If you have a more clumpy galaxy, however, like something like cold dark matter, remember cold dark matter is really clumpy, you're going to have these clumps of dark matter that are going to be hitting your stream as it's orbiting. And all of those hits from these clouds of dark matter are going to make the stream puff up. They're going to make it... Let that pass for a second. I was hoping we had enough during intermission that wouldn't happen during talk, but wouldn't be spacecrafts.
Yeah.
All right, I'm gonna keep going, I think. Can people in the back still hear me over the train? Okay, sounds good. So, the sort of puffiness of these stellar streams is actually a really good way to measure how clumpy the universe is, and this is ideally what we'd like to do. However, we're sort of in this spot where we actually need better data on these stellar streams. We need more data, we need better simulations of how this happens in order to really get down to the sensitivity of this clumpiness measurement that we need in order to be able to distinguish between these dark matter models. So, just to sort of summarize the current state of things, remember, a self-interacting dark matter probably can't solve this clumpiness problem without also destroying small galaxies and clusters as they try to merge. Fuzzy dark matter probably smooths the universe out a little too much. We see smaller galaxies than fuzzy dark matter predicts, and again, it also makes it so that these galaxies have a harder time of merging in these clusters. The jury's still kind of out on warm dark matter. Again, the only real way to make this measurement, distinguish this from cold dark matter, is with these sort of clumpiness studies I was talking about. And again, we really don't have precise enough measurements for that, so that's still a possibility. And furthermore, cold dark matter isn't really off the table yet, because as we started making better and better simulations, what we noticed is that all of a sudden some of these smaller galaxies, these smaller clumps, kind of went away. And so we think that that might have actually been a problem with how we were treating the normal matter in these simulations, rather than how we were treating the dark matter. So cold dark matter is very much still alive as a dark matter theory. So this is the sort of current state of things, and this is still quite a lot to sort out. But I do, just in closing, want to mention that we are getting some new facilities soon that should help us out quite a bit. So the Vera Rubin Observatory should hopefully be starting full-time science observations next year. That's done in Chile. It's this really nice survey telescope. It's going to take a lot of really detailed pictures of the sky at a kind of every few weeks. And that's going to give us much better data on the behavior of these stellar streams. And then also we've got the Nancy Grace Roman Space Telescope, which the most updated launch date I could find was 2027. So fingers crossed for that, although we all know what happened with JWST, so... I will not speak it into existence.
Yeah.
Thank you.
Stop.
And this is another sort of wide field telescope that we're actually hoping is going to start giving us our first good data on stellar streams in other galaxies, which is really important because the Milky Way is just one, and you don't want to make a prediction about the entire universe with only one data point, so being able to do this kind of science in other galaxies is going to be really important as well. So, even though this is a pretty crazy problem to try to solve, I think the future of dark matter science is very bright, even if the matter is not. And with that, I will leave my summary up here and take questions. Thank you.
How does the research that you're doing contribute to this question?
So the question is, how does the research I'm doing contribute to this question? Thank you, Logan. So one of the projects I worked on over a number of years was actually looking at how the satellite galaxies of the Milky Way merge with the Milky Way, and comparing that in cold and fuzzy dark matter. So some of these studies I was talking about with looking at how different galaxies merge in different dark matter models. One of those was me. And then these days I'm getting a little bit more into this stellar stream area. So I'm looking at how, again, the satellite galaxies of the Milky Way are interacting with these stellar streams and trying to puff them up. Yes?
Which theory of dark matter do you personally think is the most plausible?
Which theory of dark matter do I personally think is the most plausible? So, really good question. None of these, actually. Personally, I look at the 1/5 of the universe that we do know a lot about, our normal matter, and I think of how many different particles we have that make up normal matter. And to me, I think it's kind of absurd to assume that the other 4/5 of the universe is just one kind of particle. So I think it's probably a mix of a bunch of different stuff, but of course, we're a long way from being able to tell that. We're still trying to sort of discriminate between the single particle models, and you got to start somewhere. Yeah.
Well, what are some results from the Rubin Observatory that would help determine what dark matter is?
What are some results from the Rubin Observatory that would help tell what dark matter is? So typically what I'm most excited for are these really deep and wide field measurements of these stellar streams. So it's typically difficult to pick out the stars that are part of stellar streams from the stars in the background or the foreground. And so by taking these really frequent, very wide field observations of these streams, we'll get a better sense of how all the stars are moving relative to each other. So that'll give us a sense of, again, how many times the streams have been run into by clouds of dark matter, and it'll also give us a better sense of what streams are out there in the first place. Yes?
Do you think dark matter also has fundamental particles like how we have in normal matter?
Do I think dark matter is a fundamental particle like we have in normal matter? I think that's probably a likely explanation. Again, without being able to move past the single particle models, I'm not honestly really sure what form a multi-particle model would take, although I think if you're appealing to the same laws of physics, there's reason to believe it could, just have atoms and electrons and all that sort of stuff, but they're just dark somehow. There's been a couple theories that have been proposed like that. So it would make sense to me. I think that if it were, again, like more massive objects, we would have found them in these kind of macho surveys. So I think it's probably something a little bit less massive, like a particle, yeah. one more. I saw your hand. Yeah, so the question was, I said better simulations sort of seem to solve this clumpiness problem with cold dark matter, and can I talk a little bit more about what that means? So one of the things that better normal matter physics will give you, higher resolution normal matter physics will give you, is a better handle on star formation. Because star formation takes place at these very, very local scales that are much smaller than a galaxy. So when you're typically trying to simulate a galaxy, you can't simulate individual stars forming. But so what this higher resolution star formation gives you is a better handle on how supernovae affect the distribution of gas in the galaxy. And so what can happen is supernovae goes off, it blows a bunch of the gas out from the center of the galaxy, and that changes the density in the inner regions of the galaxy. And because you're changing the density, you're changing the gravity, and so some of the dark matter can actually kind of puff up as well, and reduce this sort of small-scale clumpiness. So that's one way. Another thing is, as we've gotten better and better telescopes, we've also just found more small galaxies in the first place, so there's a little bit of an observational bias there too. But those are a couple ideas. Is that it? Okay. Thank you.
I'm going to take MC privileges very momentarily here. Physics completely aside, do you have a dark matter model, a favorite name for dark matter model?
Physics completely aside, I really like fuzzy dark matter. It's just cool.
That's a cool name. It's a cool name.
Yeah.
Obviously, I'm a nerd. Hopefully, most of us are. But I think being able to do.
I think being able to apply quantum mechanics to really macroscopic objects like galaxies is a really cool thing to get to do that other fields just don't really get to mess with. So I really like fuzzy dark matter. It makes really pretty pictures, but it's pretty well ruled out at this point. So I think I'm a little sad in that regard. But thanks for your question.
Yeah.
Sorry, I completely stole the opportunity. Thank you all for coming to join us tonight. I hope you learned a lot about dark matter. I certainly did. I think a lot about light. I do not think a lot about dark matter. So, due to the fact that the third Tuesday in December falls approximately 3 days before Christmas, we are not going to be having a December show, because I think we would have about 5 people here. So our next show will instead be January 16th, which is the third Tuesday in January 2024. So we will hopefully see you here for our first show of the new year. Again, thank you all for coming. Feel free to come talk to us at our merch table. If you get a last drink, make sure to tip your bartender. And we will see you in the new year.